The human lifespan probably has an upper limit, and why that's good. I'm Blair Fix. We are at war with death and its causes. We are building towards an infinite horizon. Brian Johnson. A common theme in science fiction is that people of the future will live far longer than folks today. The reasoning goes something like this. Historically, human life expectancy was short, often under 30 years. But today, in some wealthy countries, life expectancy is pushing into the upper 80s. Given this trend, it seems possible that the human lifespan could continue to grow forever. Unfortunately, this thinking is probably wrong. While plausible on the surface, it misunderstands the nature of how the human lifespan has been extended. The backstory is that for most of human history, about half of all children died before age 15. For tens of thousands of years, humans made essentially no progress at civilizing this gauntlet of youth. But today things are different. With the help of modern science, the vast majority of children now reach adulthood. As a consequence, life expectancy at birth has exploded. What's hardly budged, though, is life expectancy at the century mark. Or put another way, while humans have made great strides at allowing the young to survive, we've made virtually no progress at halting the march of old age. True, we can imagine a future in which we slow aging, but today there's no sign of such an elixir. And so we're faced with a simple mathematical problem. As long as aging remains inexorable, there's likely a natural upper limit to the human lifespan. And that's probably a good thing. You see, if the elixir of life were actually discovered, the risk is that the spoils of longevity would be hoarded by the rich. Thankfully, the opposite is true today. Indeed, one of the most stunning features of longer life expectancy is that it makes the human lifespan more equal. Life expectancy explodes. To dive into the science of life expectancy, let's review some recent history. For humans, the last 2 centuries have been the anthropic equivalent of the Cambrian explosion. For thousands of years prior, the pace of human social evolution was glacial. Then, with the onset of the Industrial Revolution, virtually every aspect of the human experience changed, including how long we live. For some context, at the turn of the 19th century, global life expectancy at birth was under 30 years. Today, it's well over 70 years. Figure 1 shows this life expectancy explosion, which came mostly in the last century. Looking at this remarkable extension of the human lifespan, we naturally wonder what lies ahead. One possibility is that the pattern over the last century continues indefinitely. That's easy enough to extrapolate. On average, each new year of the 20th century brought a quarter-year extension to global life expectancy at birth. If this ascent continues, global life expectancy will reach 91 years by 2100. And by the mid-24th century, when the events in Star Trek: The Next Generation supposedly take place, global life expectancy will surpass 150 years. No doubt many folks, including me, would like to live in this sci-fi future. Sadly, it's almost certainly a fantasy. For one thing, the continued march of longer living depends in large part on continuous scientific progress, which is not guaranteed. I mean, just look at what the Trump regime is doing today. Forget new science. Trump is busy demolishing basic public health policies. If this demolition doesn't stop, Americans are almost surely going to see their life expectancy continue to drop. Let's suppose, however, that this stupidity is a brief hiccup and that scientific progress continues for centuries to come. Even then, it's unlikely that life expectancy will rise indefinitely. Perhaps the easiest way to see the problem is to look at trends in life expectancy not at the beginning of life, but near its end, where the picture is less sanguine. Figure 2 illustrates this end-of-life story. Here I've plotted global life expectancy for individuals at age 100. What's notable is the lack of progress. In 1950, centenarians could expect to live for another 1.1 years on average. In 2023, this life expectancy had been extended by just 0.4 years. In other words, despite the massive 20th century gains in the average human lifespan at birth, longevity amongst the extremely old hardly budged. It's this failure to extend the lifespan of the very old which suggests an upper limit to human life expectancy. A tale of two gauntlets. To understand the historical route to longer life expectancy, it's helpful to think of the human lifespan as having two survival gauntlets, a gauntlet of youth and a gauntlet of old age. The gauntlet of youth begins at birth, which is one of the most dangerous periods of life. Historically, many individuals died during infancy, and only about half of children reached adulthood. In other words, the gauntlet of youth was brutal. Fortunately, things have changed. In fact, reducing infant mortality is the most important factor in increasing human life expectancy. Figure 3 illustrates. Here, the horizontal axis shows life expectancy at birth, measured for every country since 1950. The vertical axis shows the rate of infant mortality, the portion of infants that die before age 1. What we find is that rising life expectancy comes with a massive decline in infant mortality. For example, when life expectancy is below 30 years, about 20% of infants die before age 1. But when life expectancy is over 80 years, infant mortality is more than 100 times lower. The secret to cutting infant mortality turns out to be quite simple, largely because the bodies of the young are designed to survive. Basic sanitation, basic infection control, and basic medical interventions at birth go a long way towards keeping newborns alive. And if children survive infancy, there's a good chance they'll reach adulthood. When we turn to the gauntlet of old age, though, the same principles don't hold. Yes, modern medicine can treat some of the downstream effects of old age, like cancer, heart disease, and diabetes. But as far as halting aging itself, science has proved impotent. And that's not surprising. Aging likely has deep evolutionary roots in metabolism itself, roots which are not easily upended. In short, unlike the bodies of infants, which are designed to live, the bodies of the extremely old are riddled with the insults of age, which is why it's unsurprising that old age mortality rates remain intransigent. Figure 4 illustrates the lack of progress. Here I've plotted mortality rates at age 99 as a function of population life expectancy at birth. Across more than 7 decades of rising life expectancy, mortality rates at age 99 are barely halved. So, yes, there's been humble progress at taming the gauntlet of old age, but it's nothing like the success at civilizing the gauntlet of youth. The mathematics of aging. To understand the limits of the human lifespan, it's helpful to explore the mathematics of aging, by which I mean the statistics associated with getting older. Sadly, age makes almost everything worse. Professional athletes are a conspicuous example. Athletes typically reach their prime in their mid-20s, after which their performance gradually declines. This pattern is known as the aging curve. By age 40, most athletes have retired. Elsewhere, the insults of aging are less visible, but still detectable. Of course, the most insulting effect of aging is death itself. From adulthood onward, the risk of death increases inexorably with age. Figure 5 illustrates the pattern in the United States. Here, the blue curve shows how mortality rates change with age. Note the J-shaped pattern, which appears when we plot mortality rates on a logarithmic scale. At birth, mortality rates are quite high, but drop quickly for the individuals who survive infancy. By age 10, mortality rates reach a lifetime low. From then on, things get worse. During the teen years, mortality rates rise, largely because teens take bigger risks than children. And from adulthood onward, mortality rates climb inexorably. This ascent marks the statistical march of senescence. Shifting the mortality rate spectrum. I highlight these age-specific mortality patterns because they're key to understanding the human lifespan. At the most basic level, life expectancy rises because mortality rates fall. Figure 6 shows this tendency measured across all countries between 1950 and 2023. Here, I've plotted age-specific mortality rates as a function of population life expectancy, shown in color. Let's run through the evidence. First, note that regardless of life expectancy, all the mortality rate curves have a J shape. Across every population, the risk of death is high at birth, low during early adolescence, and then rises inexorably during adulthood. Second, note that higher life expectancy comes with lower mortality rates at every age. This connection is a logical necessity. To live longer, people must die less. Third, and most importantly, note that mortality rate reductions are not even across ages. Instead, the reductions are large during youth and small during old age. It's this last fact that's crucial for understanding the limits of the human lifespan. If greater life expectancy was achieved by taming both the gauntlet of youth and the gauntlet of old age, there'd be hope for an unbounded lifespan. However, all the evidence points to the opposite scenario. While we've succeeded at reducing mortality among the young, mortality among the old remains stubbornly high. Figure 7 visualizes this intransigent pattern, which I've dubbed the funnel of death. What I've done here is plot age-specific mortality rates relative to the baseline for a population with a life expectancy of 35 years. This mortality rate baseline corresponds to the dashed horizontal line. The colored lines illustrate how mortality rates shift downward as population life expectancy increases. The resulting triangular shape highlights the lopsided nature of mortality rate reductions. The most spectacular mortality rate reductions come at birth. But from infancy onward, these gains are gradually winnowed away until we reach age 90 and up. There, regardless of population life expectancy, individuals are funneled relentlessly towards death. The upper limits of the human lifespan. Because the gauntlet of old age remains intransigent, it follows that the human lifespan probably has an upper limit. Here are some ways to estimate it. A popular approach is to assume that the old age gauntlet narrows perpetually until it eventually collides with certain death. With this model, we can estimate the maximum possible lifespan of a human individual. Figure 8 illustrates this method using U.S. data in 2021. Here, the blue curve shows how U.S. mortality rates rise as a function of age. To model this march of senescence, we fit the mortality rate data with an exponential function, shown in red. Then we extrapolate this function until it crashes into the mortality rate of 100%. At this point, death becomes certain, which means we've estimated the maximum lifespan of an individual in the given population. For the US in 2021, this maximum lifespan is about 113 years. While this exponential method is conveniently simple, it's also quite unrealistic. In my mind, there's no compelling reason to suppose that the human body has an insurmountable maximum lifespan. Yes, death may become more probable with older age, but imminent death is never certain, which is to say we need a more plausible way to model mortality rates during extreme old age. A better approach is to treat the gauntlet of old age as something that narrows perpetually, but never actually touches certain death. A simple way to model this narrowing is with a logistic function. Figure 9 illustrates the revised method. As before, we fit our model to empirical mortality rates during late adulthood. Then we use the model to extrapolate the pattern into extreme old age. The difference is that with our logistic model, mortality rates bend towards certain death, but never actually touch it. As a consequence, this model presumes that there's no maximum human age. Continued survival is always a matter of increasingly minute probability. While this logistic model doesn't define a maximum lifespan, it does provide a way to define the onset of the old age gauntlet, an onset that sets an effective upper bound on human life expectancy. Here's how it works. I'll define the old age gauntlet as the point when death becomes more probable than survival. This threshold occurs when age-specific mortality rates exceed 50%. In Figure 9, I've marked the gauntlet zone with the red shaded region. Now, in the United States, the empirical data never enters this region. But supposing that our logistic model is sound, we can extrapolate the trend and estimate the age at which mortality rates exceed 50%. In the US in 2021, I find that this old age gauntlet begins at about age 106. So what should we make of this onset? Well, because the old age gauntlet is a statistical concept, it says little about the survival of specific individuals. In a large population, a small fraction of people will defy the odds and live past age 106. That said, the onset of the old age gauntlet is important because it signals the effective upper limit to human life expectancy in the given population. The logic works as follows. Once individuals enter the old age gauntlet, death becomes more probable than survival, which means that their life expectancy is extremely short. It's measured in months, not years. Now, imagine a future society in which virtually everyone lives to age 105, yet the old age gauntlet remains entrenched at age 106. In this scenario, the population life expectancy would remain close to 106 simply because so few people would surpass this age. Now, we can quibble about whether this scenario is likely. If most people survive to age 105, then the onset of the old age gauntlet might get pushed back. But the point is that the mathematics are clear. The onset of the old age gauntlet sets the effective upper limit to the average human lifespan. The old age gauntlet has a sticky onset. Having defined a way to estimate the onset of the old age gauntlet, let's see how these estimates vary with population life expectancy at birth. Figure 10 shows my measurements. As life expectancy rises, the onset of the old age gauntlet slowly recedes. However, the recession has an intriguing Z shape with a curious plateau at age 102. Why? I have some thoughts about where this Z-shaped pattern comes from, but first, let's get to the bad news. Even if the onset of the old age gauntlet continues to recede as life expectancy pushes into the 90s, the current trend implies a maximum trajectory. The reason is quite simple. By definition, life expectancy at birth can't significantly exceed the onset of the old age gauntlet. But according to the current trends, the old age gauntlet is retreating much slower than life expectancy is rising, which means that the two numbers will eventually collide. If this trend continues, I estimate that the collision will occur at age 117. See Figure 13 in the appendix for more details. I consider this age a reasonable estimate for the maximum possible human life expectancy. Time will tell if this prediction is correct. Back to the Z-shaped trend in Figure 10. What causes it? One possibility is that it's an artifact of the way I've analyzed the data. I run some consistency checks in the appendix and don't find any obvious problems. But for argument's sake, let's suppose that the Z-shaped pattern is a real feature of the human experience. If so, an intriguing possibility is that the plateau region illustrates some sort of natural maximum human life expectancy. Of course, the word natural needs some caveats. In many ways, extreme old age is not natural, in the sense that wild animals rarely reach this stage of senescence. In the wild, there's too much competition, too many predators, and too many diseases for animals to reach nursing home age. So, paradoxically, the natural limits of an animal's lifespan only reveal themselves in the safety of captivity, where individuals are able to die of old age. By analogy, perhaps we can think of the fruits of industrial civilization as creating a captivity zone in which humans can live, a zone that isolates us from the insults of the wild. In this captivity zone, the human body naturally hits its lifespan limit shortly after age 100. With intensive medical intervention, the body can survive for a bit longer. And of course, if conditions of war, famine, and pandemic intervene, bodies age more rapidly. But in the safety of the captivity zone, we see evidence for a natural maximum lifespan. Am I confident in this interpretation? No. I am throwing it out there mostly as an empirical provocation. The march towards equality of life. One of the oddities of the human species is that we're the only animal that's cognizant of its own mortality. Perhaps there's a reason for that. As a rule, animal reproduction is a killing field. For example, when a female salmon lays eggs, about 99.9% of these potential offspring die before reaching adulthood. And even among our closest evolutionary relative, the chimpanzee, survival to adulthood is generally worse than a coin flip. So if animals reflected on their life prospects at birth, they might be horrified at the injustice. Of course, throughout most of human history, lifespan injustice was the norm. Many children died young, while relatively few people reached old age. Even as recently as the late 20th century, episodes of vast injustice occurred. For example, in the 1980s, South Sudan endured a brutal civil war in which food blockades were a common weapon. Tens of thousands died in the ensuing famines, with most of the toll paid by children. In Figure 11, the top panel quantifies this carnage. Here, the red curve plots the age distribution at death in 1988 South Sudan. During the depths of the famine, the majority of dead were children under age 10. In that year, life expectancy at birth was just 11 years. The good news is that such tragedies are now rare, and the root causes of childhood mortality are easily preventable. The result is that in the wealthiest countries, deaths now pile up on the opposite end of life. The most extreme example of this reversal comes from Monaco in 2023. The bottom panel in Figure 11 shows this demographic upheaval. In modern Monaco, most adults survive to old age, and the most common age at death is 90. With these two extremes in mind, we should ask ourselves why the famine in South Sudan is considered tragic, while the old age pileup in Monaco is not. Yes, the answer to this question is fairly obvious, but let's go ahead and spell it out. The human notion of tragedy seems to be tied, at least in part, to the existence of plausible counterfactuals. For example, it's tragic for children to die of starvation because the alternative, not starving, is easy to envision. Likewise, it's a tragedy when a young parent dies of cancer because, again, we can imagine a world in which the parent survived. But when it comes to death at old age, we find it difficult to imagine an alternative, science fiction notwithstanding. Indeed, for all we know, there is no alternative to biological aging. And so we don't consider death from old age a tragedy. It's simply the natural course of life. One way to frame this morality is that it describes perhaps the most basic form of human right, the right to die at roughly the same old age. Of course, nature itself cares nothing for this right, but we humans have made it a fundamental social goal, and we've gone a tremendous way towards achieving it. Let me illustrate this success by quantifying the inequality of the human lifespan, measured with the Gini index. When this Gini index is high, individual lifespan is unequal. Most people die young, while only a lucky few reach old age. In contrast, when the lifespan Gini index is low, it indicates that human lifespan is equal. Most people die at close to the same old age. With this lifespan Gini index in hand, we can quantify what's perhaps the most stunning yet under-recognized pattern in all of demography. It turns out that the task of extending human life expectancy has been a project of bringing remarkable equality to the human lifespan. Figure 12 shows this pattern. As life expectancy rises, lifespan inequality falls. I should add that this wire-tight trend is the sort of pattern that emerges only when there's no social choice involved. True, humans choose to extend our lifespans. However, the route we take is non-negotiable. We extend life expectancy almost entirely by keeping the young alive, and not by extending the lifespan of the extremely old. The consequence of this non-negotiable strategy is that human lifespan must become more equal as life expectancy increases. Now, the dream of longevity gurus is to make death at old age optional. Of course, there's no hint that the elixir of life exists, but if it were discovered, I think that it would almost surely be disastrous. Let me put it this way. Today's billionaires are able to amass extreme wealth. They're able to accumulate immense power, and they're able to bequeath these gains to their children. But the one thing that billionaires can't do is hoard lifespan itself. But what if they could? Imagine a world in which CEOs are as immortal as the corporations they command. Imagine a world in which the poor are short-lived, expendable ants. Imagine a world in which lifespan is inherited at birth. I can't imagine a worse hell. Of course, it's possible that humans of the future will be able to distribute the fruits of extended living with justness and equality. But then again, given the debauchery of today's elites, this utopia doesn't seem particularly likely. Which is to say that while I would personally be quite pleased to live much longer than a century, I am quite certain that I won't. Nor, for that matter, will anyone else. At least for now, I think this human finitude is a good thing. Hi folks, Blair Fix here. I'm a crowd-funded scientist who shares all of my painstaking research for free. If you think my work has value, consider becoming a supporter. You'll help me continue to share data-driven science with a world that needs less opinion and more facts. You can sign up at economicsfromthetopdown.com/membership.